We return now to thinking about the regression and model selection framework from the point of view that what we want to start thinking a little bit about is how do we do this in a more formal fashion, and how do we think about various aspects of the model selection procedure. What I showed you previously, for instance, was in thinking about models and the regression framework and the regularizations, part of what you'd like to go after is interpretable models that have some kind of degree of parsimony. But the question is, how do you evaluate models more formally? In fact, one of the important ways to evaluate models is how well do they do, not on the test data that you trained them on, but on, not the training data you use to build the model, but on some new data set it's never seen or had the ability to test on. So we're going to get after that today. So this is out of the book, Data-Driven Science and Engineering. You can find more information at databookuw.com. It has extensive set of lectures, and all the code used here, both in Python and MATLAB, is available to you for download. Okay, so this is a really important concept and really critical in thinking about building good models, the idea of cross-validation. Remember, you're going to take data, you're going to build a model, you're going to maybe propose a model with some parameters, and there's an input and output of that data, and then you're going to fit those parameters in that model to that data. And the real question comes is, how well does that model work on data that was not used in that fitting process? So this comes to this idea of cross-validation. This is absolutely critical in all of data science, to think about you must do cross-validation on your models for anybody to believe what you say about them. Okay? I will finish. I know you're not supposed to call anybody dumb, but I think this statement is really important. If you don't cross-validate, you is dumb. I'm going to stay with that statement. I know that you're not supposed to say those things to people, but if you've gotten this far in your math education and you're this advanced, and you can't figure that out, then maybe you got to be considering what the options are for you here, okay? So I want to really emphasize this point. Don't be a bad data scientist. Be a good data scientist. At least do things that you're supposed to do and do them right. Cross-validate, or you is dumb, okay? All right, we're going to make t-shirts with that. You is dumb t-shirts. I mean, provided you don't cross-validate. As long as you cross-validate, you're smart. Okay. So I'm going to walk through an example of this. And I'm going to show you a little example that I constructed here. It's very simple to walk through. But it's going to highlight a lot of the things we want to start thinking about in sort of this model selection architecture and the idea of cross-validation. Okay? So let me pull up a code. And here it is. Okay, so first of all, I'm going to go right back to the examples we've been working so far, which is just fit a parabola. So here it is. You know, I'm going to take 100 points on the domain 0 to 4 of x squared, right? And you can simply do something like, I don't know what the model is, so I could fit up to a 20th degree polynomial, 21st degree, so all the way up to x to the 20. This is what I'm going to fit here. And what I'm going to do is a little experiment. In particular, what I want to do is take this code here, and I'm going to do a number of trials. So I'm going to select data. So for instance, suppose I have the ability to do this. So the trials here, this variable, is I'm going to do a loop through here, and I'm going to take 2 trials of data. So suppose I do the experiment twice, and I get 2 model fits. Up to this point, what we've been doing is just give me the data, do the fit. But maybe I have different experiments, and what I want to do now is say, well, but my model has to fit all of the experiments. Maybe I have 2 experiments, or 10, or 100. This makes a big difference in the way I think about what my models might be. Up until this point, even when we did least square regression, we took one set of data, did the regression, and I showed you that if you do that, and if you take another set of data and do the regression, they can be quite different. But now what I'm going to do is say, yeah, but I'm going to vote across all those trials of data to see what kind of model I should be building. So this is what this is going to do here. It's going to do a loop to the number of trials. And what I'm going to do with this is I'm going to take now my data, which is a parabola, put a little noise on it, and I'm going to solve it with the pseudo-inverse, with the backslash, with the lasso. So 3 methods. Okay? Now I showed you before they give you 3 different results, but I'm just going to focus on those. In fact, on a single shot, the lasso did very well in picking out the parabola. The pseudo-inverse and the backslash did not do so well. But maybe I was playing an unfair game again for them. Maybe what I really should be doing is taking a bunch of trials of the data and cross-validating them with each other. In other words, they have to be consistent. If I'm measuring the same system over and over and over again, what this is allowing me to do is say, well, here's my model on shot by shot. Maybe I should average over those to see what the right model might be. So at least this first part is just to look at this thing under the idea of what happens if I take multiple trials of the data. Okay? So let's go ahead and look at this. And let's run it, this first section. Okay. What I'm showing you here is 3 sets or 3 rows here are going to be different things. So the top row is my pseudo-inverse. Second row is the backslash. The third row is lasso. And the first column is what happens if I average the 2 trials. What happens if I average the 10 trials? What happens if I average the 100 trials? So a couple things I want you to notice here. So for instance, lasso, even with 2 trials, it does really well. And then it doesn't change much with 100. It actually says, look, you have basically a parabola there. So just use x squared as your fit. That's what this is telling you. But we knew it did that pretty well before because we could do it on a single trial, and I showed you that in previous lectures. But what about the pseudo-inverse and the backslash? The pseudo-inverse, notice what happens. Remember, I had great variability trial by trial when you do this least square regression. But here, what you're seeing is, if you do 2 trials, it's pretty variable. But as you take 10 trials, notice what it's trying to highlight here. It does believe that quadratic and the cubic start to become important, starts to really pinch down the higher order polynomials. In fact, you keep going up, it keeps highlighting, expressing higher and higher this cubic, quadratic and cubic term, but again, these become smaller out there. So on averaging or cross-validating the model, it improves versus something like this. A model built from this will be awful at any extrapolation, whereas this will do better, but still clearly not as well as the lasso. Same thing here. If you do the backslash, look at the loadings that you get out of it. But if that's over 2 trials, 10 trials, look at it's really crushing down the higher degree polynomials. And then 100 trials, look how well it does in picking out the quadratic term. So not all hope is lost on these other regression, AX equal beta regression methods. However, notice how we're supplementing them now by saying what we're going to do is cross-validate these across a bunch of trials. Start building models that basically work across lots of different data sets. So that's the main idea behind cross-validation. You don't just take your data, throw everything on there and build one model. You take subsets of the data, or you take multiple tests of the data, you start building the model and either averaging over those models or selecting which model might be best across the data sets. There's different ways to do cross-validation. But here is just a very simple-minded idea. And notice how well you start even recovering something much better here in these methods that weren't, doesn't work nearly as well as the lasso, but at least you're now getting closer just by doing this cross-validation process. Okay? So that's an important little example to show, and let's build on that. So what we're going to do next is we're going to start looking at this in more detail. In fact, actually, I shouldn't have erased that. One possibility here, let me just show you one other thing here. So if I take, here's another, I'm just going to rerun it. So it's going to generate some new data. Here's the new data. One thing I will mention then is the following. This is, look at this. This is the variability over 2 trials, 10, 100. But when you get over here with these higher ones, you could start saying, what does the lasso like to do? The lasso wants to promote sparsity. So it's going to, by design, make terms 0. The other 2 terms, the others are least square fits. However, notice what it's doing. It's creating a bunch of loadings that are quite small. One can imagine easily capitalizing on that by saying, I'm going to put a threshold on there. In fact, what I'm going to do, anything below a certain value, I'm going to go ahead and set to 0. So you could imagine starting to remove terms based upon how small they are. You might say, that constant term is going to be out, maybe this linear term, all these higher order terms. I'm going to remove them because the loadings are so small, over 100 trials, that in fact, I don't think they should be there. Okay, so you could threshold it. So thresholding is very much looking like the L1 regularization over here, which is the lasso regularization. So again, this is all about regularization, right? I've emphasized this point. The objective function is clear. All these give you about the same error. It's just that they give you very different solution types based upon your regularization framework, and regularization matters a lot. And you can regularize with this L1 penalty, or you can do this L2 and then threshold and cut small terms away, and then redo it. The more data you can pull in, if you had a lot of data and it has to be consistent over huge amounts of data, you'll eventually get to x squared. Even lasso gets to it immediately. These least square fitting procedures could get to it eventually as well if you had enough data and if you start thresholding. So let's go ahead and take a look at this more concretely with the rest of this code. So now what we're going to do with the rest of this code is we're going to go ahead and take a look at some of these errors. In fact, what I'm going to do is something similar to what we did before. In the last lecture was to think about interpolation and extrapolation. So what I'm going to do is make this parabola up again, but I'm going to break it into 2 parts. 0 to 4, which is my interpolation region, 4 to 8, which is my extrapolation region. So what I want to do is cross-validate a model and see how well do I do in the extrapolatory regime. That's really what you want to do. In all of this data science, who cares about the training data I gave you, right? Because you can easily build a model that's going to work well there. The question is, if you take that model, go put it over here on new data, does it work at all? So you have to cross-validate this to make sure that it kind of works across data in order for you to go port it to somewhere else. And so this is what this is going to do here. We're going to start looking at how well can I take the model, port it over from X1, which is in the 0 to 4 region, to the 4 to 8 region, which is just a simple parabola. This is like about the simplest extrapolation possible. And yet you're going to see how hard it is. In fact, last lecture I showed you, these models, except for, they do not extrapolate well in general. So you have to always understand, am I interpolating or extrapolating? Because interpolation, I would say, is really easy in comparison to extrapolation. So this is what we're going to do, is extrapolate. And we're going to do it with these 3 methods: the backslash, pseudo-inverse, and lasso. Okay? So we're going to run this. We're going to make some training data, make some polynomials up to degree m, and what we're going to do is start computing our solutions on these and computing how well you do with your error. Okay, so let me run it. here it is. So let's run the whole thing. And by the way, I'm going to make a couple comments. So this was actually taken from the first part of the code, which is the average loadings of the three methods. So if you notice here, what I did is I took those coefficients of the loadings. I call it A1M, A2M, A3M, okay, which corresponds to the pseudo-inverse, the backslash, lasso. Okay, those are those three. I'm also going to take these and I'm going to say A total 2 is, I'm going to threshold it. I'm going to take any one of those, and any one of them that has a loading that's above 0.2 I'll keep. Otherwise, anything below 0.2 goes to 0. That's what this command does here. So now I have a different model, and I also have a model which combines the thresholding and non-thresholding. So I take my models, I threshold it, or I don't threshold it. So I have basically 6 models. I have the original 3 plus thresholded versions of the original 3. Now it's not really that important that I threshold the lasso because it's pretty much in good shape as it is. However, I just do this across the board, and I'm going to show you some of the results from this. Okay, so let's start here. This is the results that you get for the 3 different methods. What this is a bar chart, and this is the degree of polynomial right here, all the way to 20th degree polynomial. And what you're seeing here is this is the loadings after 100 realizations. So I do 100 realizations, I average them from the first experiment I did. And so what you're seeing here, the blue, is the pseudo-inverse. This is the average loadings. You can see it's not that sparse. The green, or cyan, or whatever that color is the QR, and the yellow, or sorry, is the backslash, and the yellow there is the lasso. So what you have there is 3 different solutions or regularizations of this problem, and they give you very different structure. Although, remember, when I do 100 realizations of this average, actually, you know, aside from these small terms here, it looks pretty good, right? They kind of seem to highlight that the x squared term is important, which wasn't the case if I did a single realization. But under this cross-validation where I'm doing multiple trials and averaging over the coefficients, the least square fit does better, the backslash does better, the lasso was already good from the first point because it had the right regularization to begin with. Okay, so I have that, and there's an accompanying figure, which is this one here, which is the same plot you're looking at right here, but now I'm going to threshold it. Anything below 0.2 I'm going to throw away. So there it is. This is the thresholded version. So what I do is my cross-validation procedure takes these solutions, averages them over 100 trials, and anybody who is small gets tossed. It's a different model. It's a way of doing a regularization that's a bit different, which is I'm just saying anybody who's small probably means maybe you weren't supposed to be there. If I had more data, I would eventually have that term go to 0, and I'm just going to force it to 0 through this thresholding. Okay, so there you go. And then I'm going to ask the question is, how well do these work? So those are my loadings, and then I want to look at the errors. So the errors, sorry, let me cut that off, right here. So here is the interpolation error. Here is the extrapolation error. Okay? Did I get that right? Yes, I did. And by the way, the important thing to notice here, you see that that's 10 to the, that's a big number. Okay? So if you run the code, you can actually see that font on your MATLAB. So the point is, error is massive for those two up here. And what these are zoom in. Okay? So what I'm going to first show you is the interpolation error. Notice what I'm doing here. So the first 3 here, this is the error that you get without thresholding. So this is model 1, 2, 3, which is pseudo-inverse, backslash, lasso. And then the next 3 are those 3 again, thresholded. So what you see here is if I do these models, so the first model here is a pseudo-inverse, and by the way, this is a detail of this up here. So look, the pseudo-inverse, in fact, gives you the best error on the interpolation. So it fits amazingly well, gives you the best error. Why? Because I optimized for least squares, and my measure of error is a least squares, so it makes absolute sense that, in fact, the least square errors is the best fit to the data in the interpolation regime. Notice here next to it is the backslash, which is a QR version of that. Does almost as well. Here is the lasso. But the lasso is still small, so it goes up here, but that's the lasso error. So the lasso error actually has a bigger error. Why? Because it's actually penalizing a different norm, which is the L1 norm, than you're using to measure your error. Whereas here, this one here, the pseudo-inverse is penalizing the L2 norm, which is exactly what you're using to measure your error. Okay? In any case, they all do pretty well. Now if I threshold them, in other words, let's go ahead and throw away the terms that are small. Notice that your pseudo-inverse error jumps up. It doesn't do too bad. I mean, here's the L1 error. Here's the L2. It grows, but it's still pretty small. But you have killed off some important terms, right? Some small terms, but it wants to use them to get a better error fit. Here is the backslash, not bad. And of course, your L1 or lasso error, which is almost unchanged from what it was because you already threw away a bunch of terms that are 0. So this is showing under interpolation, all of these work pretty well, whether you threshold them or not. And in fact, it shows you that this cross-validated model works amazingly well in the interpolated regime. But now let's go to extrapolate with these models. Remember, these models were built in the regime of the parabola 0 to 4. And now I'm going to go from 4 to 8. And in the 4 to 8 region, I'm truly extrapolating. I've never collected data out there. I'm trying to take my model from 0 to 4 and walk it over from 4 to 8. Well, here's where I do. So here's the errors. So first of all, the error for both the pseudo-inverse as well as the backslash are really huge. Okay? But what you're seeing next is you almost don't see anything here. Because what's next is the lasso, and then the 3 thresholded versions of our model. So if I threshold those models, in other words, things that are small, set them to 0, although the error goes up in the interpolation regime for the pseudo-inverse, notice it dropped way down in the extrapolation regime. In other words, the fewer terms tends to give you the ability to extrapolate much better into a different regime. Here's the lasso error. The lasso error didn't change too much, but it still does quite a bit better than either the pseudo-inverse or the backslash in the extrapolation regime. So this is the idea of the cross-validation. You can start seeing that if you use multiple trials, you average over them, you don't just simply fit a model one time to the data. Rather, you take subsets of the data, build the model, average. There's different ways to do cross-validation. But this is telling you that you can do quite a bit better when you do that. And even throwing away terms like thresholding can make a huge improvement in how well your model works. Okay? And if you had enough data, there is the potential that if with enough data, maybe I had thousands or tens of thousands of trials, the average of those coefficients of the higher order terms in the pseudo-inverse would go to 0, and I would just be left with the parabola. But that really assumes that you have very, very large amounts of data, which may not be the case in practice. Okay, so let's go back here and talk a little bit more then about the whole idea of cross-validation. And what I'm going to present to you here is a graphic. And this graphic is trying to illustrate sort of what I did a little bit of in that example, which is I have a data set. And one of the things you do when you take a data set, to be fair, is immediately you have to start breaking that data set apart. In particular, what I'm showing you here is a sort of a more standard way to do cross-validation, is from this data, you randomly select what's called a withhold set. You take it out of there. It is never used to train on a model on. Okay? You hide it from yourself in some sense. You say, I'm going to randomly select this, put it to the side. I never get to touch it again. I don't get to use any information about it. When I build a model, I'm going to go test it on this data that was withheld. Okay? So the idea here is you randomly select, this is going to be your withhold or test data set that you're going to hold out to the side. Now the training data, the rest of the data goes into a training set. And the training set you normally think about as a validation subset versus a training set. And what I'm just going to show you is a k-fold validation technique. So what you do is you start saying, I want to build a model from this data. So I'm going to assume that I have some model from an input to an output with some f and some parameters beta. So there they are. This is the generic representation of a model, right? So it's right here. Y equals f x b beta. So I'm trying to determine these betas from inputs to outputs. So what I do is first take one fold of the data. In other words, I go into this data that I withheld, and I randomly select some parts of that data. And with that data, then I build a model. I now randomly select from a different part of the data. That's a different fold. I build a model from that data. I do this k times. Okay, so if I were to do a 10-fold validation, I would essentially build 10 models. I'd randomly draw from the data, build 10 models in this data. And then what I can do with these data is I can do several things. So you can do something as simple as average them, right? You can do something other than that. You can say, like, well, let me take these models and see how well does each model work across the data, all this training data, that is, and I'll pick the best of those models. I'll average them, I'll threshold them. There's different ways to take these models and then build your final model out of them. So this is the cross-validation procedure. You build models, use other models built on other portions of the data, and then essentially you vote on them in some sense, in some way that you specify. But the idea is that's the cross-validation. This is sort of a schematic of a k-fold cross-validation. And then you get this aggregate model at the bottom, which has been tested, which has been built out of several models that have been unified together in sort of the best way possible. What you do with that model now is the real performance of how well you've done is you take that model, you bring it back over here, hit it on the withhold data set, and get a score. You're not allowed to make any more parameter adjustments. You just simply go hit this model on this data and say, here's how well I did. And that's the metric of success of your model. And you do this through the k-fold validation. So oftentimes, people think about splitting this data and how much data should be in the withhold, how much in the training and the cross-validation sets. And this really depends a lot on the kind of data that you have. You know, you could do a 70-20-10 split. So for instance, you could take 10% of the data, put it out here. It depends on how big your data is too. 10% might be massive, right? It depends on how much data you have here. Or 10% might not be enough out of the withhold. Okay, so it depends a little bit on the specifics of your data. So for instance, you imagine, even if I took 20% out, with 80%, I can do these folds where I say, like, you know what I'm going to do is I'm going to build a model on out of what's remaining of the 80%. I'll take the 50. So then out of that 80%, let's call it a 50-30 split. 50% I'll build a model test on the 30, do it randomly again and again and again, cross-validate on that, then test here. So there's different ways to do it, and it depends on how data poor or data rich you are, what those splits should look like. So I don't want to give any hard, fast rules because they may not apply whatsoever, okay? Especially if you go to some of these modern deep neural net architectures where the data is almost, sometimes it feels like it's unlimited data. So, you know, you just have to pick how many withhold data samples do you want, not a percentage. So this is an architecture. And again, if you don't cross-validate, you is dumb. This is the only way to say how well did I do in a model. You cannot come to someone and say, hey, I did really well in a model. Unless you've done this procedure, nobody will believe you. Nobody should believe you. You shouldn't believe yourself. Okay? So make sure to get this right. This is very important. Otherwise, you're going to be making erroneous assertions and not using your data correctly. Okay? So that's the kind of generic procedure. So I'll finish here. So this is cross-validation. And what it's allowing you to do is start to evaluate your model. So the last thing I want to do, we've been talking a lot about models, and all of this is leading up towards how do we do a model selection. So what I've been showing you is parsimony, cross-validation. These are really important concepts, and I want to end in the next lecture on information criteria. But for this lecture and other lectures, you can databookuw.com, and you'll find all the lecture notes there. This is a link to the PDF of the book, as well as code base in Python, in MATLAB. Lots more videos, not only of this chapter, but all the chapters of the book, all available for download and for free. Next lecture, model discovery, or cross-validation of the models and information criteria.